Okay, so thank you very much, everybody, and thank you very much to the organizers for this wonderful workshop and for inviting me to be here and speak to you. So I'm going to talk today about a quite old problem, which remains, I guess, pretty much interesting. And I'm going to show you some new numerical results, which I think have interesting implications and may open new questions and give some good insights. So as you imagine now, the problem I'm talking about is Fourier law and its anomalous properties in low dimensions. By the way, this work has been done in collaboration with Pedro Garrido at the University of Granada in Spain. Okay, so Fourier law. As you probably all know, Fourier law describes heat transport in a material subject to a temperature gradient. So it says something like this. No? So the heat current flowing through the material is just proportional to the temperature gradient, and the proportionality constant is just what we all know as the heat conductivity. This kappa here, which is a key material property. Here you have this there are many reviews, many interesting reviews. Here you have some of them where you can find out a lot of things about Fourier law. This is already a pretty old problem. Fourier stated this law in 1822, and it's 2015, and though it's very well characterized at the macroscopic level and experimental level, to date we don't have a first principle microscopic Hamiltonian derivation of Fourier law. So it's an open problem. As your law it's put in a paper, Fourier law is a challenge to theorists. So things get even more interesting when you go to low dimensions. In 3 dimensions, even if you don't know how to derive this conductivity from first principles, you can measure it in experiment, and it's very well characterized. When you go to low dimensions, it's funny because you have some interesting features. You have anomalous heat transport. That means in particular that this conductivity seems to depend on the system size. In particular, for one-dimensional momentum-conserving systems, this kappa is believed to scale with the system size, to diverge with the system size as a power of L to the alpha. This is, of course, a very interesting question for a theorist, but this also has a lot of experimental and technological implications. These anomalies have been measured in real materials. The most noteworthy probably is graphene, where in 2D you have also some mild anomaly, but you can also measure this type of anomalies in heat conductivity for, I don't know, nanowires, nanotubes, even polymer chains, and I think even in spider silk, this type of anomalies has been described. Okay. So there are many open questions. The first of them is probably, I mean, what does it mean? This means that Fourier law just does not hold, does break down in 1D, or rather there exists some generalized Fourier law or anomalous Fourier law in long dimension. If you look at this, it looks like a first-order expansion in the temperature gradient. So does Fourier law hold only in the small temperature gradient limit, or is a very general law which holds for large gradients too? And moreover, in 1D, is this anomaly universal? I mean, with this I mean, is this alpha a universal exponent? So I'll try to answer some of these questions today for a particular model. Okay, so as you can imagine, there has been a lot of work in this field for quite many years, both from the theory side and from the numerical and experimental side. At the theoretical level, there has been recent theoretical breakthroughs in the form of nonlinear fluctuating hydrodynamics. We have been told these days a lot about this beautiful theory. And this theory can be extended to talk about the correlators of the currents, and in that case, it predicts universal behavior and Kardar-Parisi-Thang in the Kardar-Parisi-Thang universality class. In particular, for these one-dimensional momentum-conserving systems, generically, it predicts that the conductivity should diverge with the system size as L to the 1/3, and that should be universal. There are, however, some exceptions which are well characterized by these G matrix coefficients. For instance, when you have a zero pressure and even potential, it's known that this alpha should be 1/2 rather than 1/3, but this is well characterized. On the numerical side, there has been a huge amount of works by many good people, all of them really impressive, which overall seem to support asymptotically the overall picture. However, most, if not all, of these works are based on linear response theory, which essentially needs a very large system size and very long time limit, which at the end of the day in simulations is never really attained. So we keep discussing about how are the asymptotics in this problem. So there are typically two different approaches. One is via non-equilibrium steady-state simulation, where you fix the temperature at the borders, and then you increase the system size. As you increase the system size, the gradient goes to 0, delta t over the system size goes to 0, and you can define the conductivity for a given size as the current that you measure times the number of particles over the different temperature. On the other hand, you have the equilibrium route, which where you measure the Green-Kubo conductivity using Green-Kubo time correlation functions for the heat current. These two approaches has been undertaken for many different models: FPU, hard particle, Lennard-Jones, 5-4, TODA, rotors, harmonic, even in the quantum realm. And there are many authors. Many of them are here. I hope if your name is here. If not, sorry. And however, I would say that yet there is no conclusive results. We keep discussing about whether the asymptotic is right. Maybe you would see something else if you go to longer times. So it's kind of difficult. The idea here is to present a fresh look at this problem. So I'm going to show you results for standard one-dimensional model in this Fourier business. But they are not based in linear response. They are based in a very simple scaling picture, and which, before entering into detail, it's general in the sense that it does not depend on going to a linear regime. So it's valid also in the fully nonlinear to very high gradients. So let's see this scaling picture. It's based on a very simple equivalence. So let's assume that you have a model or a system which obeys these three equations here. So on one hand, we are going to assume that our model, our system, obeys Fourier law, which in this case means that the current is just minus some conductivity, which depends on the local fields, rho, density, and T temperature, and it might depend on the system size times the temperature gradient. Okay, that's Fourier's law for me now. Let's assume also that our system tightly obeys local, macroscopic local equilibrium. And with that, I mean that locally, at any point in your non-equilibrium system, the equilibrium equation of state relates density and temperature profiles, okay? This is a strong statement, but it's a macroscopic statement. I'm not talking about local equilibrium at the measure level, so it's more at the macroscopic level. I'm writing here just the ideal gas equation of state, but this should be general. This is, I mean, the model I will study has this simple equation of state, but this is completely general. So imagine that locally you obey the equilibrium equation of state, where this P is the pressure. Let's imagine also that our system, the heat conductivity of our system obeys this simple scaling form, which might look at the beginning a bit strange, but this is the standard scaling that one would expect for this type of model. So this square root of T over mass, I mean, can be deduced with just dimension analysis, times some function of the density, which is unknown, times this L2 alpha, which is in principle, the possible size anomaly that the system shows. Okay. So the statement is the following. So if these three equations hold for my system, then this is completely equivalent to the following Scali's laws. So both the density and the temperature over pressure profiles follow from a single universal master curve, f of u, some u, whatever. And this function is really universal. It doesn't depend on the system size, on the temperature gradient, on the average density, on anything. It's a universal master curve for your model. These profiles follow after a linear scaling of space, where this psi is just some reduced current. This is the current that you would measure, the square root of the mass, over the pressure to the 3/2. Okay? So these two statements are equivalent. So let's, it's very easy. So let's look at the.
Any boundary condition already or not yet?
Yeah, in principle, I'm thinking of a system coupled to two different thermal baths at the boundaries. Okay? So it's fluids or lattices driven out of equilibrium by boundary baths at different temperatures or you know. Okay. So, okay, so let's look at this equivalence. So with using.
The pressure is constant throughout the system, right?
Yes.
That's what it says.
Yes, yes. Yes, I need pressure to be constant. So, but in these cases, I mean, if you don't have, you know, gravity, then it should be okay. Again, it's a very general, it should hold for any d-dimensional lattice or fluid as soon as these three equations hold. So let's look at this equivalence. So using local equilibrium, we can relate temperature and density profiles point by point. So let's use local equilibrium to write Fourier law in terms only of the density profile, okay? So who is T? T is P over rho. So we use that here at the conductivity to write the square root of T as a function of the density, and we plug all these density dependence here, and then we arrive to the following different expression. It's equivalent to Fourier law. So this is essentially this J square root of n over Prada equal to some function of the density times the derivative of the density. Okay, this G prime is K rho times rho to the minus 5 over 2. Okay, whatever. The key point is that you can interpret this as a G prime, the derivative of some function of the density. So you can write down this as the derivative of G over X. So that immediately implies that G of rho of X, whatever G is, that we don't know yet, we don't know how to relate it with these unknown functions, whatever G is, the G of a given of any density profile will be linear in space. So psi X over L to the alpha plus some constant, where again this psi, remember, is this reduced current. Typically, when you measure profiles, they are well behaved. So we are going to assume that this G is again well behaved, so it has a well-defined inverse. So immediately you see that if you use this inverse, the rho of X will be some function, which is essentially the inverse of this G, of this linear scaling of space. And using local equilibrium, then you see that Tx over P has to obey the very same similar scaling with the same function. So there is a universal master curve, which doesn't depend on the boundary conditions, on densities, on L, on mu, some parameter that I will use later on, some mass ratio, doesn't depend on anything. So from this master curve, any density profile follows after linear scaling of space. But you can also go the other way around, because this is in fact an equivalence. If this holds, then you can very easily prove using the same arguments that these three equations should hold. So if I have a model where I measure profiles, density and temperature profiles, and I find this type of scaling, then I would prove these three equations, okay? In particular, any measured steady state profile should be collapsed into a universal master curve by scaling a space by the reduced current that I measure in my simulation and shifting the profile a given constant in the x direction. You will see how it works later on. Okay, so this is an equivalence. So if I see this hold, if I see this in my experiment, these three equations should hold exactly. Okay. So what's the objective? Our idea was just to test this scaling picture. And the nice thing is that it can be used to measure with very high precision the anomaly exponent. And why is that? Because the collapse of our profiles will be very, very sensitive to the right anomaly exponent. If you are not using the correct anomaly exponent, you won't find any collapse. And minimizing some distant functions, you will see later on, you can really measure with very high precision the anomaly exponent. Again, I'm not assuming at any point linear response. So everything is, I can be arbitrarily far from equilibrium with very high gradients. So it takes full advantage of the nonlinear character of the problem. Okay, so which is our model? So our model is a canonical one, which has been studied many, many times in the literature. It's the diatomic hardpoint gas. So this is a Hamiltonian model. You find it in one dimension where you have point particles. These point particles have alternating masses. So the odd particle has mass little m, let's say 1, and the even particles in the chain have a big M mass. So, and this big M is larger than 1. So this model is characterized by the mass ratio between the two particles, okay? And this is what I call mu, the mass ratio, which is always bigger than 1, okay? I have n particles, a system of length L, so the average density is this eta, n over L, And I couple my fluid, because this is, you can see that's a fluid, to two stochastic thermal walls at the boundaries. So every time a particle collides with the wall, it comes back into the system with a velocity randomly drawn from the appropriate Maxwellian distribution. Okay? So as soon as these two temperatures are different, so you are into the Fourier law type of setting. No? You have a temperature gradient, you have a current, and then let's look at what happens. Importantly, this model is fully aerodynamic, so it has at least 3 conservation laws. So it conserves local density, momentum, and energy.
So only the light mass is connected to the heat bath, right?
In this case, yes, I always use, the light mass, but it shouldn't be important. Shouldn't be important.
So the heating only comes from the boundaries.
Yeah, yes. The bulk dynamics is purely Hamiltonian. And in particular, it's why this model is interesting, because the dynamics is really simple. So you have just ballistic motion in between collision with your neighbors. So this is very efficient to simulate. That's one of the advantages. This one and the stochastic heat bath is very easy to implement. The dynamical rules are very simple. You have also another nice feature, and it's that this density temperature separability. You can see this hard point potential as a limit of inverse power law potentials when the exponent go to infinity. And for this inverse power law potential, you can prove that any system magnitude should be separable. Should exhibit density temperature separability.
Because the particles are points.
Yeah, are points, and they have like a delta potential, so they cannot overcome each other. So this order is maintained. So this light heavy. This order is maintained throughout the evolution. So it's truly one-dimensional. So this means, for instance, that the equation of state is really simple. In this case, it's just ideal gas, and that the heat conductivity can be split into square root of T times a function of this is density temperature separability, which is helpful. It's not essential, but it's helpful for the analysis. Okay, so then we measure density profiles, temperature profiles, pressure, current in the bulk, in the walls, all sorts of typical observables that you can think of. We measure them, and we measure them for a very large number of system parameters. So we run simulations for 5 different system sizes, from very small, 100 particles, to relatively large, 10,000 particles. We run simulations for 4 different temperature gradients. So we fix the right temperature to 1, and we change the left temperature. So we go with left temperature from 2 to 20. So we go from small temperature gradients to pretty high temperature gradients. We study also 4 different densities, from 0.5 up to 3, and 8 different mass ratios. So we study this mu, which is the ratio between the big mass and the small mass, from 1.3 up to 100. So we really explore the whole, parameter space. This amount to a total of 640 simulations, so they run for a few months in our computers. So here you have some of the details. So we took care. Here, these pictures have error bars, but you don't see them because they are much smaller than the symbols. So they have 3 sigma error bars. So here you see, for instance, some results for the temperature profile and the density profiles for mass ratio equal to 3 and the left temperature equal to 2. Okay, and these different curves are for different densities, global densities, 0.5, 1, 2, 3, and the different colors mean increasing n. So you can see here many things. Profiles are highly nonlinear, and we have, as usual, as everybody knows, strong finite size effects. So you see here how profiles really move with, and they change with the system size. Okay. So we do that for many different boundary temperatures. Again, they look similar, but they are not. So look at the scale. So we are going 20 to 1, 10 to 1, 5 to 1, different densities. This is just mass ratio 3, but we have equivalent data for 8 different mass ratios. Okay. So again, nonlinear temperature profiles and strong finite size effects. However,
when in temperature you have bigger discrepancies than in density?
well, you have this. Yeah, it's a good question. Well, I don't know. You have discrepancies also in density, though they don't look. If you look here, for instance, for this point, you see the different colors, and there is a big.
Maybe the scale.
Yeah, it's probably the scale. The density profiles are very steep near the.
Since the one in the inverse of the other.
Yeah. So that's the thing. Let's check local equilibrium. So we have local temperatures, local densities, we have pressure, so let's check local equilibrium. So here I'm plotting.
When you define the local temperature, it's just the local kinetic energy?
Twice the average of the local kinetic energy over the average number density. Yeah, so that's.
When you go very nonlinear, do you ever look carefully to see if it locally satisfies Maxwell?
Yes, you cannot see. I mean, you know that the real measure shouldn't. I mean, it should have 1/L corrections to Maxwell. This is the. I mean, if not, you wouldn't observe current. I mean, the current needs these corrections to local equilibrium. But if you do the measurement for 1 month, you are unable to see the differences in the tails. It's very hard. But then you can look at space-integrated observables, because these corrections are small, 1/L, but they extend for long system sizes, long correlations. So when you integrate over the system, you can look at those corrections. For example, the second moment of the total energy has a correction when compared to the local equilibrium expectation. This correction goes as delta T squared. And this has been predicted in some stochastic lattice cases, and you can observe it also here. But this local equilibrium is at the macroscopic level. So I'm looking at the equation of state. Are rho and T related via the pressure that you measure? And the answer is yes, to a very high accuracy. So here you have T over P, plot versus rho for all this data. All the points are here. And you see what you would expect, the 1/rho law that comes from the ideal gas equation of state. This is just the equation of state as a function of rho. And you see it's 1 plus minus 10 to the minus 3. So I mean, we see local equilibrium at the macroscopic level. However, notice that the thermal walls, essentially, you can think of them as a infinite mass particle, which is sitting there and it's perturbing the structure of the fluid. No? So we want to, in order to study this scaling, we want to remove this boundary effect. So we are going to remove some boundary layers. So the first point at the left and the right, we are going to drop them before doing the scaling analysis, okay? Sorry, let's see how it works. But I'm gonna show you, I'm lazy, so I didn't want it to do the movie again. So I'm gonna show you how it works, not for this model, but for another model. And this is helpful because it will show you that it's really a very general feature. So I'm gonna show you how this scaling works for a two-dimensional hard disk fluid, which is a very similar model, but now it's 2D. So you have, again, two-dimensional disks of a given size. They collide elastically with one each other. Hamilton dynamics holds in the bulk. And then you have two stochastic heat baths here at different temperatures. This is the hot bath, and this is the cold one. So let's run simulations for a given density, 0.5, and for 8,000 particles. And then let's look at the profiles for different temperature gradients, from very small to very high. So those are the density profiles, okay? As you increase the gradient, so you know high temperature, low density, low temperature, high density. Now let's subtract the boundary layers. So we remove these guys here because they are affected by this wall. Okay, now we make a zoom. And now let's scale. So remember, space has to be scaled with the current over the pressure to the 3/2. This current and this pressure has been measured in each simulation, okay? So those are the profiles after scaling the space. And now let's apply the shifts. I don't know what are the shifts, but I know how to measure them. I shift until optimal collapse. No? I can measure it, so I can really measure. So we are shifting all the profiles to see whether they are coming from some universal curve. And yeah, it looks like they are coming from something universal.
For alpha?
Sorry?
What do you have to choose for alpha?
So again, this is 2D. In 2D, let's say that we don't have anomaly. We have logarithmic anomaly, but this is for a fixed n. So here there's no alpha. Alpha will come later on for when we come back to Bondi. Now the same thing, but for a fixed big temperature gradient, but different densities, from very low to very high. We apply the scaling, the current that we measure with the pressure that we measure to the 3/2, top. And now we start shifting profiles. Let's zoom to the left so you can really see what's going on. So here there is no alpha. The key point is that we need alpha. So you see that it didn't look like, but at the end of the day, seemingly, yes, all those profiles, which are, again, they are measured with standard techniques in hard disk simulations, so they follow from a single universal master curve, which is this one. So here, I don't know, maybe we have 1,500 data points. So it's a really huge amount of data. Okay, so the idea is let's do this, but in our one-dimensional case. So, but now remember, we have this size anomaly. So we have to scale also with L to the alpha, and we don't know which this alpha is. So for a fixed mass ratio and a given alpha, that whatever you do, you give a number, and then we plot the bulk density profiles versus this thing here. So the current, so the position scaled by the current over the pressure to the 3/2, both PK and GK are the ones that you measure. This mass is 1, so forget about it, times L to the minus alpha, where alpha is this number that you have fixed, that you don't know, okay? Recall that the reduced current looks like this, and we are looking for a scaling like that. So what do we obtain? So this is what we obtain for our one-dimensional model. All these gray curves are the profiles, density profiles, once scaled with this psi L to the minus alpha before the shifts, okay? So here you have data from all simulations, so from 5 different system sizes, 4 different temperature gradients, 4 different overall densities, but for a given mass ratio, okay? Once we apply the shifts, all of these curves fall down into this beautiful universal master curve. I had to make the point small, yeah.
You have 2 free parameters. I guess you measure, right, the pressure, right?
Yes.
That you measure, and current.
And the current, yeah.
So zeta and
Zeta,
alpha are free parameters?
Alpha is fixed. Let's say, of course, I'm showing you the nice picture in the sense that for the good alpha, and zeta are just these shifts that that I fit. This I fit. Yes, that's right. Yeah. Okay, so if you use the correct alpha, you observe this. Sorry, but I have to say it's a beautiful scaling. Sorry. Moreover, we already measured the shifts for the density. So now we use those shifts to scale the temperature profiles. And here you don't have to fit the shift. You already measured them. And with those with the shifts of a density profile, you obtain this scaling for the temperature profile. So everything fits.
And what is alpha? What is the number?
Okay, so I'm going exactly to that point now. So, okay, if you change alpha, of course, the picture won't be as nice as this one. So this is telling you why it's a high precision method. So we can define some standard collapse metric, a standard distance between different curves, which is normalized very well. It has been used for many years in simulations. And then we obtain these shifts by minimizing this standard collapse metric versus the shifts, okay? Once you have the optimal shifts, you have a distance for a given exponent alpha and mass ratio mu. So what we do is to minimize this distance, d of alpha mu, versus the exponent alpha, okay? And how this minimization, how it looks like. So this is just answering your question. So this is the best collapse that you can obtain after shifting. So this is the optimal collapse for 3 different alphas. So this is alpha 0. This would mean normal transport. So you see that our system has no normal transport. This would be alpha 1/3. So this would be what one would have expected within the Kardar-Parisi-Thang picture of heat conductivity. And it's not bad, but you can see that it's either, okay, it's not bad, but of course, when you compare it with this alpha, which is 0.297, and you can really measure the precision of this thing to the 3rd decimal, you see that, I mean, this is much better than this one, okay? No, each curve has its own shift, which is related with boundary conditions. But the nice thing about this is that you don't, those shifts, you just fit them from this procedure of moving the profiles along and minimizing or optimizing the collapse between different curves. Pretty much. Yeah, I mean, you have a huge span of shifts. Okay?
Does the optimal alpha change with the mass
Yes, that's the point. That's where I'm going. So this is the optimal alpha. So that's why I'm calling this violation of universality, in the sense that within the nonlinear fluctuating aerodynamic picture, we expect that this alpha should be universal and should be this 1/3, which should belong to the Gardner-Pace-Time universality class. And what we see, again, to a high degree of precision, is that the alpha that we fit with this method, which is again independent of linear response, so we are going to very high temperature gradients, everything, is not 1/3, and it depends non-linearly and non-monotonously, sorry, on the mass ratio. So it goes from being small, near 0.1, it goes close to 1/3, but not quite, it's just 0.3 almost for mass ratio 3, but then it goes down again, and it seems to converge to 1/4. This is like 1/4.
When mu is 1, so when
the system is non-ergodic, because when mu is 1, in a collision particle just exchange velocities. If you forget about the boundaries for 1 second and you leave it in a microcanonical, so close, the initial velocities wouldn't change, and it has ballistic transport. It's a singular model, so to say. Well, probably. Yeah, I think still you would have. I'm not sure. I wouldn't. It's really singular. So you see, no, when the masses are the same in 1D, when they collide, it's as if they crossed, because they don't. They exchange velocities.
Sorry, I have same as Sanjeev's question. So it looks like, I mean, you have more than, I mean, you have many fitting parameters, no? I mean, this zeta, I don't understand this shift. How many fitting parameters are there here?
I mean, there is, one for one of those profiles, but the fitting parameter is just the amount of shift you have to do to collapse with all other data.
So for each profile, you have two. You have alpha and zeta.
Let's fix alpha. So there is some alpha that I fix at some point. So for each profile, I have a shift that I have to do to collapse with all other data. Okay.
Okay.
And now, but this collapse can be good or bad. Even when I make the optimal shifts, the collapse can look like this, like that, or like that. So then, once I find the optimal shifts, I still have some spread. So I minimize this spread as a function of alpha. So how does this distance function looks like? So it's like this. So this is mass ratio, this is alpha, and this is this distance function as a function of alpha. Okay, and notice here the logarithmic scale. So this distance function has a very deep and very narrow minimum at a given alpha, which is essentially telling us this point here. So this curve here is this one here. Okay? And the width and the depth of the minima tell us something about the error parts of our measurement.
Pablo, you could also measure an alpha by just considering how, for the given mass ratio, the heat current depends on L. Would that give the same values you get from this?
No, because in that case you have, and I think you're going to understand that later on, you have still the boundaries going on. So this trick of subtracting the boundary layers and let's look at the bulk is important because essentially what this is telling us at the end of the day is that this is the universal master curve. So this should be the master curve that you observe in the infinite size limit, where you can really imagine that you can solve the problem exactly, and then you go to do thermodynamic limit. You should obtain this curve. So what this nice collapse means? It means that for all our simulations, profiles in the book correspond to profiles of the macroscopic system. Okay. However, what we see is that so those profiles correspond to the profiles of a macroscopic system, but subject not to the boundary temperatures that you are putting with your walls. They are subject to some renormalized boundary conditions, which are affected, and those are very strongly affected by finite size effects. So you will see later on how we can really see that the theoretical predictions agree with the profiles, but the boundary conditions really change and move within.
Well, a technical question.
Yeah.
How did you define the boundary layer that you need to get rid of?
This is intuitive. In fact, for hard disk, it's you always see in the profile there is like a jump in the densities, mainly in the densities, also in temperatures. In 1D it's more tricky because they spread much more. So we are safe and we remove like 6-7 points in each point. I think if you go to
Independent of L?
No, no, no. So we remove always the same amount of. So that's one of the points, that similarly these boundary layers are important even if you go to, I mean, they decay very, very, very slowly. I would say logarithmically
You
or.
should remove a finite fraction.
Yeah, yeah, I agree with you.
You should do finite size scaling properly and remove a boundary layer that's proportional to the length.
Yeah, yeah, yeah.
In 2D, it's not so.
No, I mean in 1D.
In 1D,
In 1D,
in 1D
yeah.
it's a possibility.
Okay.
Because you should introduce a finite size scaling error if you don't scale the boundary layer in proportion to the length. You should scale everything in proportion to the length.
Yes, yes, but
Everything you do to the data.
but again, those boundary layers seems to scale like, I mean, log L. So they really don't go away for two. I mean, I'm exploring from
Right, they're
100.
proportional to the size of the system. Right. They have a long tail. Right, so you should scale it, which means cut away, say, 10% and 10%.
No, but this is no, they are not proportional to L. This is what I mean, or to 1 over L. They are scaling with the system size as a very weak logarithmic fashion. So I prefer just to keep them constant because I move into order of magnitude.
Both ways and make sure your exponent is independent of how you do it.
Yeah, that I agree. So, but let me continue and try to convince you that it's right. Oh, okay. So okay. So in principle, this would mean that, I mean, your exponent depends on mass ratio. So let's say violation of universality in the sense that for this model, at least, we don't see universality. It doesn't mean that that does not hold in other models. I don't know, but in this model, we don't see universality. So how the scaling curves look like? So here you have the scaling curves. I've shifted them in the upwards direction just for clarity for the different mass ratios. In each one of these curves has this 1,880 data points. Again, measured for 5 different system size, 4 gradients, and 4 different densities. And I mean, I don't see finite size corrections at all in these curves. Those are the density scalings, and those are the temperature scalings. And these are the exponents that we measure. Now, this alternating mass diatomic model has very nice scaling properties. So if you scale temperature with some constant, then you know that the conductivity should do something, and so you can use these scaling symmetries, and I have to thank both Abhishek and Henk for pointing out this argument. You can use these symmetries of the system to show rigorously that whatever your conductivity is should be something like a square root of t times a function of the adimensional parameters, which in this case are just the number of particles or mu. Okay, but with this scaling, I've shown you that because we are looking at this, we are testing the scaling picture. This is telling you that the conductivity should be something like this: L to the alpha times a function of the density. In order to make these two things compatible, there's only one option: is that this function of the density is just some constant times the density to the alpha, to the exponent alpha. Okay, just dimensional analysis. This density has dimension of 1 over L. So in order to make this dimensional, you need this dependence. Okay, so let's check this prediction. So then we go to our profiles. We take the current we measure, the L with the correct alpha. We make the discrete derivative of the profile, square root of t, and we test it. Okay, and here you have this function k rho that you can measure as a function of rho in a log plot. So you see that all of them are powerless, as predicted. Okay, and you can fit the exponent, and the exponent is this beta, which is within error bars to a high accuracy equal to alpha. Okay, but now what is nice about this observation?
You can see something weird going on there.
Yes.
It's like scalloped.
It's like a.
It's like curve.
Yes.
Curve.
Yes. Yeah. Okay,
That's a
but
typical feature of deviations from scaling.
the thing is that I have to do this. This is the derivative of the temperature profile, and I have to do it numerically, and I don't have many cells.
So why are there like 4 batches?
Okay, because I mean, you have like, let me see. So these are the like density 0.5, density 1, density 2, density 3. This gray data for mu equals 3 before scaling with L.
Right.
So you see that all of them have more or less the same slope. They are noisy, I agree. And I said, typically say this.
I guess I'm looking at the bottom where you can see the curve.
Yeah, so again, this is mass ratio, which is very high. When you go to the high mass ratio, relaxation is low, so errors are bigger, so things get messy. But okay, so this agrees. Sorry, I'm gonna finish quickly. The next thing about this is that now we have a expression for this k of rho, a to the times rho to the alpha, and this allows us to solve the macroscopic problem. We can solve the whole thing at the macroscopic level. So this is the G prime. So G will be something like this with this number. So which is the universal scaling function? It's just 1 minus u over this nu star times to our exponent. Okay. Let's check. You can also solve the temperature profile, the density, the pressure, and the current in terms of the control parameter, which are the boundary temperatures, the average density, and everything. Okay. Well, there is some bound on the current. This has an asymptote at some point, and this implies a bound of the current in terms of pressure, but it doesn't matter. But now we can compare theoretical prediction of the macroscopic theory with our data. And probably you don't see them, but here you have lines. And those lines are this master curve that we just predicted, and they have only two input parameters, which are the exponent that we have measured before and the amplitude of those curves, which both of them depend on mu. Okay, and the agreement is great. And here you have also the curves for the temperature profiles. You can compare the temperature profiles with the prediction, and here is where this boundary layers thing comes. So the theory predicts that T of x to the 3/2 minus alpha should be linear in x, but without giving a slope. With a slope which is given by the current over the pressure to the alpha times this number times L to the minus alpha, and you can check that prediction. So we do that for all profiles for small n and big N. And then we see that in all cases, when you use the current that you measure, the pressure that you measure, all agree. So those are profiles of the infinite macroscopic problem, but not the profiles that you would expect for the temperatures that you put at the wall, but for some other temperatures, which strongly depend on on the number of particles. How these temperatures go to the T0 at the wall? Extremely slowly. This is where I'm telling you that it's like log. I don't know, but it's not log, it's slower than that. You can test the predictions for the current, so everything agrees as far as you take into account that boundary temperatures are not the temperatures that you are setting at the walls, but something else, which depends on the system size. Okay, so this is telling us that Fourier law holds exactly even for a system of size 10 to the 2. I mean that this law holds for a system 10 to the 2. And that it holds also for very high gradients. So that means that Fourier law is not just a small gradient law, but there are no higher order Burnett-like corrections in heat conduction. It's telling us about these bulk profiles are really the infinite system size profiles, but with n-dependent boundary conditions. And it's telling us that for this model, universality does not hold. There are many questions, but okay, we'll keep working on this. So thank you very much for your attention.